In topology, fine. Otherwise, we do it here. This is what we do. Because it have beautiful topological consequences. In other words, if it is true in all metric spaces, so it should be also true in R3 actually. Okay. It should be also true in R3. Now, Rn and R3. And this has, particularly really important consequences. So, in other words, something that I am holding in my hand is a compact set. Isn't that a compact set? Because it's closed. It's compact. So, sphere is a compact set. Torus is a compact set, subset of R. So lots of logical objects, lots of geometrical objects that you have in R3 that you have to deal with in R3, they are insightful. So let's move ahead. Let's try Okay, so let's recall the definition of complexity. Okay. What is the definition of compact set? That a set is compact if for every cover you can find a finite spot. Open. Cover is going to be open. They call the subset of R is compact. Every open cover, say U alpha, and also the stuff. So you can say I. There exists finite of. There exists a finite. So of this U1 and such that some cover. What was the meaning of being cover? So it's like I'm going to say that that's a cover for T if the union of T's contains T. Subcover in the cover itself, it means that this is the one. Roughly, we can say that this is compact. Why? Because I can cover it with loads of then I can select some specific box out of all these boxes. That finite in quantity and going to cover you. Not getting into detail because we have discussed it already. What were some examples? Some examples of rational numbers is compact. Is it compact? So Z is not compact. Okay, one of the things. Like this is an important thing for every open curve. Okay. So proving something compact It's not going to be an easy task because you have to verify this condition for every open. But disproving something not being compact is something very easy. Just take a cover and show that it doesn't have any finite. That is not compact with respect to the immediate cap. Not compact. Why not one? Imagine I have this. 1 minus 1. When I take difference of epsilon of each of these things, and I collect all these neighborhoods in a set, so that is going to be a cover for setting open cover for Z. But just think about it. If from that collection, I just remove one. This. If I'm going to remove this, there is no way that the remaining set is going to cover this. So, in other words, this cover is not even have a subcover actually. Forget about finiteness. Doesn't have even subcover. Because if you remove something out of it, it's going to just think about it. If I'm just removing one neighborhood, like I said, that's my U0 and that's my U1 and that's my minus 1 and so on and so forth. So my cover is UZ, and where N is belongs to Z. And I'm saying that in a subcover, I need to remove few sets from it. I'm not removing loads of sets, I'm just removing one actually. Just removing not. Now can this new set be a cover for that? So this is going to cover everything but not cover.
Step 0.
Because you found a cover, cover which doesn't even have a subcover. Finite. That is not compact. If it's not compact, you can show that these discrete sets, infinite discrete sets, notable, they are not compact. Interestingly, finite sets are compact.
Right. Mr. Mohan. Identification.
If you remember, what we said actually, or what we discussed in detail previously, is that compactness is kind of a second best thing to be finiteness. It's a version, it's a relaxer condition. So if you want something to be finite, it's like you are having a huge restriction. But this compactness is roughly like finite, but it's not necessary that the set which is compact should be finite. You can have infinite compact sets, right? But finite sets are examples of compact sets.
In R2 and ordered set, notation.
Huh? You can think of an compact set. Give an example. So why finite sets are compact? So if a set is finite, just think about it. If a set is finite in a space, how is it going to look like? So it's going to look like some particular. Imagine now I have lots of open cells.
Yes.
It's like that's an open curve, no matter what open curve you do. Okay. From this open cover, I can always use a finite subset. Why? Because just think about this point. This point is a point in your set, and this open cover is covering your set. So that means that this point is going to lie in at least one of the open sets. You can't say that, okay, this is a point which lies in none of open sets. Because if this is the case, then the set is not going to be covered. But then this collection is not going to be covered actually. Okay? So I have lots of open sets. So I'm saying that just choose those open sets which contains your points. Take this one, take this one, take this one, take this one, and take this one. Okay? So this collection of double circles, these are open. Okay? And put them in a set. It's going to be the subcover, okay, of the cover, and this is going to indeed a subcover bar because it will contain the number of points. Then there is no need to find basically. Why? Because if the subcover itself is finite, then you can choose. If a cover, if cover itself is finite, then you can choose itself as a subcover actually. So there is no need to find. You need to be careful. Definition does not demand actually that this set I should be finite. This could be an uncountable set actually, not even countable. In a cover, you should have an arbitrary number of open sets. So if you are just taking finite cover and you are trying to find its subcover, is not going to work. You are not satisfying the definition. In order to satisfy the definition, you need to take arbitrary cover. So there are lots of open sets. And we are saying that finite sets are compact because out of these open sets, we can just pick those balls which contains all points, okay, of your set. So since the points are finite, these balls are going to be finite. As well last time. Wasting my time and doing something like that we did because it's good to keep happening with it. Let's do another example. Can we have an infinite compact subset? Answer is yes. Just need infinite compact subset. Consider this set.
Yes.
I discussed it previously, I'm going to discuss it again for the same reason. So, well, yeah, don't worry. Take it. 10 minutes at least more. Okay, so one more n where n is a set of natural numbers. And plug 0 into it. And my claim is that this set is common. This set is common. Okay?
Yes, sir.
Right.
We discussed it previously when we were discussing the definition of compact.
Discussed it.
Yes.
Let's recall it why it should be common. Another one.
So
So how this set is going to look like? So imagine I have 0 and 1. I have 1/2 here. 1/3 here. Like 1/2. 1/3 here. Rough here goes to take 1/4 here. 1/5 here, and so on and so on. Closer and closer and closer. my claim is that this set of discrete points, which is not even an interval actually, is a compact set. Right? Let U alpha such that alpha belongs to I is a cover for C. Okay? There's a cover for C. What is a cover? How can I have a finite subcover?
There is going to be a neighborhood of 0.
Exactly. We're going to say that if it is a cover of C, then obviously there exists some U alpha such that
0.7.
0 belongs to
U alpha.
For some answer.
Now, how this U alpha is going to look like? This U alpha is going to be roughly like an interval. So imagine it is something like that. So it contains 0. So it's going to contain 0. But interestingly, it's going to contain lots of basically terms of this set as well. And how many? Actually, infinites.
Will be left outside.
So it contains infinites. So it's like I can say that there exists a number after which all terms of this set, including 0, are in this neighborhood. Imagine that number is, say, n. So that after instant n, all terms of this sequence and 0 are in this set. So just think about it, what is happening before n. So there are only finite terms which are outside this neighborhood. So what we can do, on every finite point I can take a small neighborhood. Okay. So imagine after n you have basically all terms here. So you're going to have n minus 1 points outside. So you just take n minus 1 neighborhoods which contains all left out points and this neighborhood.
Yes,
So you're going to have a finite subcover containing, therefore, okay, is it making sense? I'm just giving a kind of a intuitive proof, but it's really. And we can carry on with this next time because we recall compactness. The 0 is a crucial. The 0 is not in the center. 0 without any, the problem is going to be. Okay, let's remove 0. Let's remove 0. So, if we remove 0, okay, what's going to happen? I mean, if we assume that Anna-Borel theorem is true, then you can answer it like that. Why? Because we have a sequence which is converging to 0 and its limit is not in the set. It's not closed. So it's not closed again. Therefore, it's not complex. It's much easier. But we can also think it before without referring to basically Anna-Borel theorem. Okay?
You cannot define it. You cannot define it.
You cannot have
Finite subcover.
take cover.
No, obviously you need to cleverly find a cover
Discuss
for which you can have that, okay,
If we remove zero, we
सर वैसे ही कर सकते हैं जैसे हमने इंटीजर के लिए किया, वैसे ही कर सकते हैं जैसे हमने इंटीजर्स के लिए किया था, क्योंकि ये डिस्क्रीट है।
सही बात है सर, वही मतलब हर एक 1/n जो एलिमेंट्स है सारे फॉर्म उसके लिए एक एक इंटरवल बना दे,
फिर एक रिमूव कर दें, वो कह देंगे ये देखो।
Same argumentation as that. That's a discrete set. So discrete sets. So actually what we cleverly did is that, okay, this is a set which has only one limit point, and that is 0. So we just inserted it. And therefore it becomes closed actually. And it is bounded itself. Right? One action. So we'll carry on this very interesting result. Okay, so when are we going